Hi, welcome everybody. This is Miss Gray and Mr. White. Hi, Mr. White.
Hi, Miss Gray.
And we're going to talk to you about the gas laws. This is podcast 9.3 in our Unit 9, The Nature of Gases. Today, our job is to work through the gas laws, which will summarize the behavior of gases, how the gas properties will change when we change the conditions. And we're going to evaluate specifically these conditions of temperature, pressure, and volume. These three right here. I can't draw a straight line, Mr. White.
That's getting pretty close,
so
though.
pathetic. Okay, um, we'll do better next time I try
We
to draw a
will.
line. Sorry, guys. We're moving on. Oh, don't draw dots. Get my cursor.
We need the arrow there.
Need the arrow. We got it. So let's look at basic properties of gases. Let's move this out of the way so you guys can see. There we go. All right, so we know that gases are compressible. What would that mean, Mr. White, to be compressible?
Well, it means you can get into a really small place and be packed in together.
Right, exactly. Um, you could call this squishability.
Squishability, that's good.
I like that word.
I like squishability.
Yeah, squishability. In other words, there's a lot of empty space between gas particles. They're not even touching one another. So we got a lot of room to squish them together.
Exactly.
Right, so compressibility in our world,
Kind of
squishability.
like a sponge.
Right, right. There's a lot of empty space in there.
Yeah.
Right, so we can squeeze a gas into a much smaller volume. So that means the factors affecting gas pressure is going to be, first of all, how much gas you got.
Yes.
How do we measure the amount of something?
Well, we always have moles.
Exactly. That's probably the easiest way, right? Because you don't want to count each individual atom.
Yep.
That would take
That
forever.
would take way too long.
Exactly.
I don't have too much.
So,
I don't have that much time on my hands.
yeah, me neither. But our students know how to work with moles.
They do.
Good.
They do.
So they'll be proficient at that. They'll be
Yes.
experts at that.
Yep.
There's also volume. If we put it in a smaller container, it's going to squish more.
Yes, it is.
Yeah,
Yes.
definitely. All right, let's see if I can move
That
this
makes
out of the
sense.
way for you guys to see. Temperature. What happens if we heat up our substance?
Particles are going to start moving a lot faster. Because they
Right.
just get hot.
Yeah.
Particles move around a lot more.
Sure. And when they move more, I don't know where to put that so it's not in the way. When they move more, they collide more because they have more kinetic energy.
Right.
Not only do they bump into each other more, but their collisions have more energy in them too.
Exactly.
So, if that was us and we collided, it would hurt.
It would.
And if we collide with more energy, it'd hurt more.
It hurt more.
Exactly. So let's get our arrow back. We can go on to summarize what happens with gases when the temperature changes. Or, no, this one, the temperature doesn't change. Let's keep the temperature constant
Let's
for a
keep it
while.
constant.
See, with Boyle's law, if you don't want something to boil, you have to keep the temperature constant. So, we're going to keep the temperature constant for now. We'll talk later on about what happens when the temperature changes.
So we're just talking about the amount of space in this one, really.
Right. So let's suppose we have this gas, and there's space on your note-taking worksheet for you guys who are listening and following along at home to draw this picture into your little box. So that first box, the biggest box, needs to have
How many do we have here?
6 little dots, it looks like. And you need to have 6 little particles in your box. But your arrows don't have to be going exactly the same direction as mine. You just need 6 particles in your box, randomly spaced throughout. So now that we've got those, let's assume that in this box we've got a volume of 4 by 4, say,
Yes.
and a pressure of 1 atmosphere. So as we change what happens to the size of our container, we're going to keep the same number of particles. So moles are constant.
They are.
Okay. And then what else is constant? Temperature.
Well, the temperature is constant because we don't want it to boil.
Right, exactly. So we'll keep the temperature constant and the number of moles of gas constant.
Right.
All right, let's change the size of the box. You ready for this?
All right, here we go.
There it goes. Now we
So yeah.
have
Twice as small, or twice as small as the first one was then.
right, twice as small is the same as half as big.
Exactly.
Yeah. So what's going to happen? Look how our particles look now, Mr. White.
So we packed together now.
Yeah.
That squishability.
They got squished together. And because they're closer together, I think they're probably going to collide a lot more with one another.
Oh yeah, definitely.
Yeah, for sure. And no, if you were paying attention to the size of these arrows, of their velocity, they're the same
They are.
because the temperature is the same. So the velocity hasn't changed because the
moving just
temperature
as
hasn't
fast.
changed. So they're
Exactly.
moving the same velocity now, but now they're closer together. They're going to collide more, I bet.
Yes.
So our pressure is going to go higher because
Yes.
it hurts more.
It hurts a lot more.
Yeah.
You have those collisions happening.
Right. So if our volume is half as much, our pressure is now twice as big.
Twice as big.
That makes sense.
It does.
Cool. Well, let's see what happens when we get a smaller box. Now it's only 1 by 1. So we took it in half again.
I bet they have a hard time moving now.
Yeah, well, they're still going to zip
They're-
around
they're
at
still zipping
500
around.
meters per second. That's
'Cause
the
the others are-
average speed of a gas particle.
Right. Plus the others are still the same size.
Right. The
So-
particles are the same size.
So it's still going the same speed.
And our temperature is constant,
Exactly.
so they're going the same speed, but our box is half as big. So our pressure will be twice as much as it was before.
Yes.
But, we're 1/4 the size that we were
1/4 the
initially.
size. So
So now 4 times as much
four
as
times
the
as much
initial pressure of 4 atmospheres.
Right.
That would give us 4 atmospheres now, because we were at, I said 4. We were at 1 atmosphere before. I'm getting myself all twisted around.
Yes.
I got my tang tangled. Pardon me.
That's okay.
Yep. So we see this relationship between pressure and volume. Pressure and volume have this kind of inverse proportionality, inverse relationship.
That kind of means opposite, right?
Right, opposite. So let's make a graph. Oops. Look, you guys have instructions too in your notes. You need to sketch a graph. So I gave you the x and y axes for this. Let's put a label on that axis. So let's put volume on the x-axis. That means as we move from left to right, what happens to the volume?
Gets a lot higher.
Right.
Or bigger.
Right. So going this way means volume is increasing. And we'll put pressure on the y-axis. And so as the volume gets bigger, what happens to the pressure? We'll start here.
Well, if it's bigger, then you're going to have less collisions.
Right?
So if you have less collisions, it's going to have smaller pressure.
Oh. Wow, it didn't like me doing that. Okay, so less pressure
Yes.
as we get a bigger volume. That makes sense, because
It
that's
does.
like the opposite of what we said before. When the volume got smaller, our pressure got bigger. So if our volume gets bigger, the pressure
Goes down.
goes down. Great. Well, in math, we summarize an inverse relationship this way. The pressure is proportional, and I shouldn't really have an equal sign. I should have a proportion, right?
Right.
It's proportional to not the volume, but 1 over the volume, because it's inversely related.
Yes.
And we could say the same for the volume compared to the pressure. And here's that graph that I prepared ahead of time to make sure we're doing this right. Here's the right answer.
It looks like just what you just drew.
I love it.
Our
when I get it
prediction was right.
Yay. Good. I like it when I get it right.
Yay.
Good. Well, then let's do some other manipulations with Boyle's law.
Okay.
Let's go from one pressure to the other. Go back to the graph. Here's our graph. So if I start out at volume 1 and I go to volume 2, then how do we describe the change from one location on our graph to the other?
Well, the volume's getting smaller from 1 to 2.
Right, and so our pressure also changes. This should look familiar to all of our students out there because they already know that the slope is going to be the change in y over the change in x.
Actually, I said that backwards. Volume's getting bigger. I said the volume was
Did you
getting
say
smaller.
it backwards?
I did.
I should pay attention
I
to what
did.
you say.
Because I said the volume's getting smaller, but the volume's getting bigger.
See,
right?
I meant what
Big
you
going the
knew,
other way.
so we're okay.
Well, okay.
Yeah,
We were still on the same page.
right. So, okay, let's translate the change in y. What do we mean by that? Normally it's y2 minus y1, right?
Yes.
y2 minus
Yes.
y1. And then the x change, we want to do that the same way or we get the wrong answer, right? x2 minus x1.
Yes.
Well, by 1 we mean the first x, the
which
first
is your
volume.
volume.
The first volume.
So
has a
x
volume.
is your volume.
Yeah.
Yes.
And then by 2, we mean the second of those conditions, right? The second volume or the second pressure. So here we'd have P1 and P2. So we're going to utilize this relationship and how we write the equation of a straight line so that we can put it into an equation format. This is the job of scientists, really, is to figure out what's the relationship between two variables. That's
Right.
what the scientific method is for, right?
Yes.
And we like to express those relationships with the graph of a straight line because it's easy to work with.
It is.
I learned it like in, I don't know, 9th grade, 10th grade.
Yeah. Ninth grade, I think ninth grade algebra.
Right,
10th grade algebra.
right,
It's familiar.
definitely. I wasn't very good at algebra when I was in 9th grade, though.
No?
No, somebody told me my sophomore year that he wrote down everything that the teacher wrote on the board.
Really?
Like everything.
Wow.
Because that's how you take notes, he said to me. You just write down
Just
what
write
the
down-
teacher writes. And I said, everything he writes down, you write down? Yes, that's what taking notes is. I had never taken notes in my life until my 10th grade year. Can you believe that?
No.
I didn't know I was supposed to. So ridiculous. All right, so here's what
Wow.
Boyle's Law looks like. Now you all know some secrets about me.
Secrets about Miss Gray.
Yeah, how did I get A's without ever taking notes? I'll never know. All right, so here's Boyle's Law. Remember, we had x1 and y1 and x2 and y2. Well, our x-axis was volume and our y-axis was pressure. So it's the same thing. So P1 represents our initial pressure, and P2 is the final pressure. And it's the same for volume, where V1 is the initial volume and V2. Right. V2 is the final volume.
Is your final volume.
Yeah. So I've written the equation in a couple of different ways. So you can see it just takes a little bit of algebra to change this into this. See, I solved this equation for the second pressure, and since it's multiplying V2, then I have to do the opposite of multiplying.
So you're just arranging the equation based on what you want to look for.
Yeah, so I'm going to divide both sides by V2, and that moved V2 down here into the denominator.
Right.
So I can solve for whichever quantity I need. If I want my final volume, then I just rearrange the equation so that final volume, V2, is standing alone by himself, right? And we use algebra for that.
Exactly.
It's a good thing our students are so good at math.
It is.
Yeah, they rock at math.
They are awesome at it.
Yeah, well, let's do a math problem.
Okay, let's do it.
And you've got the calculator, but I'll run a
Okay.
calculator on the screen and you'll check my math.
All right, I have it turned on, so we're set to go.
That's always a good step. I hate it when I put the numbers in and it's not even turned on.
Like, it's not even on yet.
I know, punching away on the buttons. All right, so the practice problem says we have a pressure of 1 atmosphere and an initial volume of 8 milliliters. So if the volume increases now to 10 milliliters, what's the final pressure going to be? So
Okay.
let's set up this problem first by identifying, hey, it's Boyle's Law we're going to use, right?
Right, and we want to
And-
find the second pressure.
Yeah, so we're going to rearrange the equation so we can get the second pressure. Just like before, that means we're dividing by V2 on both sides, dividing by V2. All right, so I'm going to remove that writing so we can see that step. Here it is. And now, since we know what all these quantities are, they're listed up here, we're just going to put them in the right place. In the place of P1, we write 1 atmosphere. In the place of V1, we write 8 milliliters. And in the place of V2, we're going to write 10 milliliters. Do you think it's important, Mr. White, for us to change milliliters to liters in this case?
Well, in this case, since they're both milliliters, then we're going to leave it the same as, since they're both the same unit, then we won't need to change back to liters.
Right, because then that math that we do in the numerator would be canceled by the math we do in the denominator.
Exactly.
So that would be a waste of time.
So what?
Extra steps.
Yeah.
I'm not into doing extra work.
Right, exactly. It wouldn't be wrong, but it's definitely putting more effort into something that we don't need to.
Right, well, let's not do
Yeah.
extra work. I like to do math that's easy. That's
Me
my
too.
philosophy.
Me too.
Okay, so in our calculator, I'm going to multiply by 1, but I think I can do that part in my head.
I think so too.
Okay, I can probably do all of this math in my head, but I just want to show, okay, here's our steps, 8 divided by 10, because the V2 is in the denominator, that means divide, right?
Yes.
And so we could have done that math in our head.
We could have.
Yeah,
Especially since it's out of 10.
Yeah,
We know that 8 tenths is 0.8.
right.
Yeah.
Oops, I want my arrow because look, I have the answer here. You were looking at my shadow. Did
Oh,
you
what?
cheat by looking at my shadow
I
there?
didn't. I didn't cheat. But
No. You think some of our
it is,
students might have?
no, we have honest students, don't we?
Of course we do.
We do.
Yeah,
I'm sure.
they're
I'm sure they didn't
honest.
see the shadow.
No.
They didn't look at
And
the
if they
shadow at
did,
all.
they solved it all on their own.
They did.
Of
They did.
course.
I have faith in them.
Me too, sort of. All right. Charles' law is another gas law. So now instead of keeping the temperature constant, this time let's change the temperature. And
Okay.
we'll see what happens to the volume when the temperature changes. But we can't change everything all at once, right? So we're going to keep the pressure constant. Oh, that's an equal sign. The pressure
Yes.
is constant. And let's keep the moles of gas constant. We'll just be
Right.
talking about like the same number of particles.
Right.
So we'll let N stand for the number of moles. We're going to keep that constant.
So we have the same number of moles and the same number of particles floating around in our gas.
Right, and the pressure is going to be the same. So now we're going to change the temperature and see what happens to the volume.
Right.
So our first job is to make a prediction. Oh, my writing's in the way.
So let's make a graph.
Okay,
Okay.
so here's our graph, an x-axis and a y-axis, and this is printed on their handout so they can fill in a graph too. Let's put temperature this time on the x-axis, because I bet we have more control over the temperature, right? If we can heat something up
We
or
can.
cool it down.
Yes.
Yeah, it would be really hard to change the temperature by adjusting the volume.
It would be.
Yeah, now I know
is
how to
really
do
hard to
that
That's
because I'm a
good.
chemist.
That's where you roll.
That's right. You know, when you're a chemist, your job is to manipulate the universe
It is.
to your will.
Yes.
Yeah, or at least be able to describe how you would do such a thing. Right. Okay, so now let's increase the temperature of our gas. Let's say you have a balloon, right?
Okay.
And you heat it up.
Heat it up.
What would happen to the volume? I'm going to start like somewhere here.
So if we have higher
Oh, I did
temperature,
that the last time, remember?
there it is again.
Okay, quit doing that. All right.
So now if we're going to heat the particles up, that means
Right.
the particles are going to move
We
a
can
lot.
get less volume or more volume? Should
Well-
our line go up or down?
I'm going to say it goes up because if the temperature is going up, that means there's going to be a lot more collisions because the particles are really moving around a lot more.
Right. Temperature corresponds to the average kinetic energy
Right.
of our particles.
Right.
And so that means kinetic energy means they're moving more. More collisions takes up more space.
Makes sense.
Yeah. In a balloon, you know, that container can expand
Mm-hmm.
and it can increase the volume. In a soda can that's closed,
Close the
not
container?
so much.
No.
Don't heat those.
No,
Yeah, we don't want to change
unless
that
you want to make a
temperature.
mess.
Right.
Yeah.
Notice though how this slope is constant. It's a
Yes.
straight line, right?
It is.
Well, that's pretty handy. Since the slope of this line is constant, we can use it like we did before with the Boyle's law.
Mm-hmm.
And how do we find the slope of some line? The change in x over the change in y.
It is. That rise over run.
Yeah, and so we're going to be using that same idea again, where we have x2 and y2. Only since it's temperature and volume, we call it v2 and t2 and
T2.
v1 and t1,
The TV.
tv. Clearing that writing so we can read this. Charles' law is related to the Kelvin temperature of the gas. And when I reveal this equation, you guys will see why kelvins are important.
Yes.
Oh, gotta have my arrow to click. Here's this equation. There it is. Notice how temperature is in the denominator here.
Mm-hmm.
It's V1 over T1
Right.
and V2 over T2 because remember it's rise over run. So we gotta put our rising over our running. And what would happen if we had a 0 degrees Celsius? Could we
Well,
put 0 in the
That's
denominator?
undefined. So would that mean that the universe implodes?
Yeah, I think that's what Miss Kincaid teaches
Yeah.
her math classes. If you have a 0 in the denominator, the universe implodes.
Yes.
And quite frankly,
That's not.
I don't want to be responsible for that. So instead of putting Celsius, we'll call this 273 kelvins.
Right.
Then we won't have a 0 in the
Then
denominator.
we won't.
So if we just used our Kelvin temperatures instead of our Celsius temperatures, we'll never have a 0 in the denominator, right?
Right.
Then that
Yep.
will be brilliant.
And I bet I know what our students all know what 0 degrees Celsius of a gas represents. Because that's a pretty standard temperature, isn't it?
Right, that's part of our
Okay.
STP.
STP.
I hope they remember that.
I hope so.
Well, we'll make sure they do.
Yeah.
Good.
That's
Hey, look,
good.
here's the graph that I drew ahead of time. Does this match what you predicted?
It does. It
Yeah,
goes up.
the line's going up, and our temperature's in kelvins. That's a good thing.
I love it when we get it right.
Me too. Happy day.
Yay.
All right. Oh, I don't need to write anything here. We're just going to look at the summary of Charles' law then. Doubling the Kelvin temperature of a gas sample.
Okay.
That would mean we're going to double its volume because they are directly proportional.
Makes sense.
All right. Then if we reduce the temperature by 1/2, then the volume decreases by 1/2.
Decreases by 1/2.
Yeah. In pressure and volume, with Boyle's law, they were inversely related. So we doubled one thing and it halved the other. But
Exactly.
this way, we double one thing and it doubles the other because they are directly proportional. Cool, let's do some
Let's
math.
do it practice.
All right then. So here's what I teach my students. I teach them to underline key terms. When they see numbers, that's probably important information.
That's a good idea.
So let's say a sample of gas occupies 3.5 liters. We're going to call that our volume because volume is measured in liters. So we'll call it B1. And then this one looks important. That's a
Looks like
temperature.
a temperature.
Okay, we'll call that
T1.
T1. And what volume? That's a question, right?
It
What
is.
volume? So that's our target. That's what we're going for. So we always circle the target in my class because targets are round. So we circle them.
Okay, that's a good idea.
You got to know where you're
You
going.
do.
Yeah, or you'll never get there.
Exactly.
All right. And then here's another, let's see, that's in kelvins, 200 kelvins.
So it's temperature.
Temperature. All right. Should we call it
How
T1?
about temperature 2 since we already have temperature 1?
Good plan. T2.
Okay.
All right then. So what are we going to do with these fancy numbers? Charles' law says that, oh, that's just the list of the things I
that's just listing
underlined.
what they are, yes.
I get confused. There it is. There's
There's
Charles' law. It says that V over T is constant.
Yes.
That means V1 over T1 is going to be equal to V2 over T2 because it's a constant.
It's always going to be in that same proportion.
Yeah, exactly. Hey, proportions.
Ooh,
I bet our students know how to solve proportions.
I bet they do.
Well, you know what? We could rearrange and solve our algebra for this. Or let me rewrite this one over here so it looks more like a proportion. 3.5 over 300 is equal to our unknown,
Right.
V2, over
That's
200. So remember that method of cross multiplication?
Oh, yes.
You cross multiply to solve a proportion?
Yeah,
That would totally work here.
it would. Totally.
Yeah. And so I tend to solve for V2 just using algebra, and that's what I've done here. But this is algebra too.
It
If
is.
you just do the proportion,
Right.
we should get the same number.
That fits.
Yeah. So tell you what, let's do that.
Okay.
So we're going to get our calculator, and we're going to do 3.5 times 200,
Okay.
because that's cross multiplication, and then we divide by this other
Divide by
term,
the second one.
right?
Yes.
Okay, let me get my calculator up too, so that we
Okay.
can follow along.
And
I
I'll
have
double
to
check on mine too.
Toggle.
Oh, there it is. Well, there is a
It was
calculator.
hiding out. Trying to sneak away. All right, so I said 3.5 times 200. It takes forever. And I'm going to hit enter here because I want to make sure I do that multiplication first.
Right.
And now let's divide by our other term, right? Divide
Right.
by 300.
Divide by 300.
And I got 2.33.
I did 2.3 repeating.
Okay. And this answer says 2.2 liters. So I don't know what I was thinking when I wrote this slide, but I think
Must be a little
2.3
typo.
seems, yeah, maybe so. Or maybe it was some sort of rounding thing I did for some odd
be.
reason. I don't know. But let's just call this
2.3.
How many sig figs do we want to keep?
Looks like we have two. We have 3.5 liters.
Yeah,
in the
technically
question.
this temperature would be 1 sig
Oh, that's
fig,
one,
but
yes.
our book publishers don't pay as much attention to sig figs as I do.
Right.
So let's consider this to be 3 and this to be 2, and so our answer is limited to 2. So this 3 is not big enough to make any difference. We're not going to round this up.
Right.
We'll just go with 2.3 liters.
and leave it there.
Do you like that better than 2.2?
I like it. I like it a lot better than 2.2.
Yeah, I think it makes more sense.
Yes.
All right, good. We're in agreement. That's all it takes. You
It
and I have
is.
to agree. Who cares
Exactly.
if the universe agrees with us? We're
As
right.
long as we do all right,
Yeah.
and we're good to go.
Oh, let's get rid of the writing now. I always forget to do that. And then we're on the next slide and it looks dumb. Oh, well. I've looked dumb in class before. This is not the first time.
Hard to believe that one. I don't see it.
All right, here we go. 1 liter. Part of my job, Mr. White, is to teach humility. And I get plenty of opportunities to do that.
You and me both.
All right, here's my other number. Let's see. This one was liter, so I'm going to call that V1. And here's our first temperature because it says from 22 to 100. So we'll call this T1. And
And the
here's
second
our
temperature.
T2. And here's our target, new volume.
So we're looking for a volume.
Right. So again, I circled the target, underlined the important information, and see what I've done here in my first step? It says volume is equal to 1 liter. That temperature is in my way. Can I
It
scoot
is.
him over?
There we
Yeah,
go.
we'll just move him out of the way. And then the temperature here was 22 degrees Celsius. But I don't want to use Celsius.
We don't.
So I changed it to 295 Kelvins.
Yeah.
And here's how I did it. Anytime you want to change a Celsius temperature to a Kelvin temperature, you just have to add 273,
Right.
and you've got it.
That's a constant, huh?
Right. And see this circle here we use for degrees? We don't use it for kelvins. We never put a circle here because that would be wrong. Where
Right.
did my pen go? Sheesh.
There it is.
There, yeah. So we're not going to put that there because that's not the right way to write
Right.
degrees.
Because Kelvins are not measured in degrees.
No, it's just an absolute number.
It is.
Yeah.
Yes.
Okay, so let's do that for our other temperature too. Our V2, we don't know what it is, so I put a question mark there. But T2 was 100 degrees Celsius. And I could do that math in my head.
We could.
Yeah, add 100 plus 273. I got that.
There you go.
Cool. Oh, here's all this. Too much.
Charles' Law again.
Okay, here's Charles' Law. Here's what we need to see. This is what we're going to use to solve this problem is Charles' Law. And then we just put the numbers that we had for V1, 1 liter, and for T1, 295 kelvins.
Right.
I think a cross multiplication should work here again.
It could. Set up
Yeah.
like a proportion again.
Right. Or I could just look here and see V2 needs to be by himself.
Mm-hmm.
And it's being divided by 373 kelvins. Well, the opposite of divide is multiply,
Right.
right? So, whoops, I want to multiply the whole thing, not just that little piece. You might erase, or because if you make a mistake, I think you should fix it.
Absolutely. That's why it's always good to do things in pencil too.
Right. Good advice. Okay. Is that going to write with a pen? Yay, got my pen back. Okay, so let's multiply this whole term by 373. And if I do that on this side of the equation,
And you have to do it on the left side as well, don't you?
definitely. So we're multiplying this side by 373. I don't have a whole lot of room there.
It's
do
getting
I?
kind of tight now.
Yeah, that's
Your volume's going down.
Hey,
You
but
got
look,
less volume.
I can, I can do this math here. 373 times 1. I don't need your support for that.
Don't need that one?
No, you can run the calculator for the next one though,
Okay.
because I don't want
I'll do that. I'll
to
double check
divide
that.
373 by 295.
Okay. So we have 373 divided by 295.
Yeah,
And I get 1.264. How many significant digits do we have in it?
let's see. We
Question.
started with
Looks like
only 2. I think
2.
we should adjust this answer then to fit
So
2
one,
sig figs.
right. So 1.26. We're down to 1.3.
Right, because
Would
the
you agree?
6 is big enough to make a difference here.
Right.
So we better call it 1.3. Good. I'm glad we're watching out for sig figs. Those are
Yes.
important. All right, let's clear the writing. You think they got it written down? If
I think
not,
so.
it's a podcast.
In
They
fact,
can pause
they can
it.
pause it, exactly.
Right. So if you need more time to write this,
Go ahead and push
push
pause.
the pause button. All right, I'm
We'll
clearing.
wait for you.
We'll be here when you come back. All right, moving on. Hey, here's another gas law.
Okay.
Okay, so far we have changed the temperature and we've changed the volume, but we haven't compared the pressure to the temperature change.
Okay.
Last time we just compared temperature to volume,
Right.
right? So now we're going to keep the volume constant, and let's also keep the moles of gas constant N is what we use for moles. The number of moles is why that's there. So that's going to stay constant too.
Okay.
All right? Because we want to be dealing with just the same number of particles. I can't cross my teeth. Oh, I know, that was pretty whiny, but I felt kind of whiny right now.
Sometimes you have the need to it.
Yes. So if the temperature increases, then the pressure increases.
Right.
That's what the Kailua law says.
Makes sense.
And y'all probably noticed this name. It says Gay-Lussac's law.
What,
Well,
is that a happy guy?
not a happy guy.
Not
He's
a
a
happy guy.
French guy. And so, I mean, we're not in the deep south. We're not going to call him Gay-Lussac. He's French. He's Gay-Lussac.
God knows that.
Right.
Right.
So we don't have to make any jokes about anybody's sexual orientation.
No.
It's Gay-Lussac.
It's Kailua.
Right. Plus, it's not school appropriate to joke like that.
No, it's not.
No. So here's the rule in mathematical terms, that when the pressure changes, the temperature changes. And when the temperature changes, it makes the pressure change too.
Right.
So when you heat it up, it gets more pressure.
Right.
Direct proportion.
Makes sense. More collisions.
Right.
Things
And
moving faster.
we don't have to do a graph because I think they get it with the whole slope and the 1 and the 2 and all
I think
that.
they do.
Yeah. But we're saying here, since these two are equal, we're saying that the slope is going to be constant
Right.
because we have a straight line relationship again.
So another proportion.
You want to try
Another
one?
proportion, sure.
All right, let's do it. And my
There's
writing's
numbers
there again.
again still.
Ah, someday I'm going to figure this out. All right, I'm going to underline important stuff. 2 liters is a volume, right?
Right.
Okay, calculate the temperature is my question. So circling my target, temperature. STP,
That's probably an important thing, I bet.
but it's just letters. It's
Just
not
letters,
numbers
though.
like this, right?
Just
Yeah,
letters.
So, but what do those letters mean?
Well, that's millimeters mercury, isn't it?
This one's millimeters of
That's-
mercury.
That is.
Do you know what STP stands for?
So that would be standard temperature and pressure?
Okay, so what temperature is that?
Well, that is at 0 degrees Celsius
Right, so
and
in
1 atmosphere of pressure.
Kelvins, that would be 273 kelvins.
Right, because you have to add 273 to 0.
Right, and what pressure is that? You said 1 atmosphere?
1 atmosphere of pressure.
Do you know how many millimeters of mercury that is?
That is.
We learned that in podcast
We did.
9.1. That was a couple of podcasts
It was.
ago. 1 atmosphere is equal to 760
That's right.
millimeters of mercury. So
I always forget that second one.
I know. Everyone at home who is also wondering what that was, they could flip back to that podcast
They could.
9.1.
Yeah.
But we'll give them a lot of chances to practice with that in class so
Right.
that they don't have to look back anymore. They'll remember it once we're done practicing.
Once you will.
Yeah. All right. You want to call this our temperature 1 or our temperature 2?
Well,
Let's
it's going to 920 millimeters mercury.
Right,
So
and it
that should be
says,
a pressure 2.
right, so this is our pressure 2,
Right.
920. And it says this 2 liters is at STP, and then it's subjected to a pressure.
So
So
that must be our volume.
this is our initial
temperature
conditions.
1, right?
Right, and then E2 was 920. And I didn't type this one out ahead of time. So if we mess it up, there's no checking our answer. I bet if we mess, if we'll check one another, but if we do this wrong, we'll have some reliable student that will show us later on.
I bet so.
Yeah, they're pretty good at
They
figuring
are.
out how I mess up. And I really appreciate those proofreaders we've got out there.
Me too.
Okay, so every time I have my first pressure, I have to put that over my first temperature. My 1 has to be lined up like this, right? And my second temperature
Same with your 2s, right?
and my second pressure. So they have to line up here. And have you noticed in all of our gas laws that temperature is always in the denominator?
I have.
Yeah, that's always going to be true, and that's pretty handy because then you don't have to memorize all the laws. You just have to know that temperature is going to be in the denominator. So if temperature is an important factor, it's going to go on the bottom, right?
That must be why we use Kelvin too, since it's the denominator.
Right, exactly. We don't want any zeros down here.
Right.
So let's put numbers in, huh?
Okay.
And then we'll do cross multiplication.
Cross multiply.
So I have 760 for my first pressure, and that's over 273. And I could put units in here, but they wouldn't really have a whole lot of meaning for us because millimeters of mercury divided by kelvins doesn't mean much to our students, and
Right.
it doesn't mean much to me either.
And it's
quite
not
frankly.
crossing out like you are on a tea table.
Right. And then we have 920 millimeters of mercury. See how my pressures are both on top.
Right.
And then this is the one that I don't know yet. You ready to do some calculation?
Okay. So you want to do a multiplication first, so you cross multiply your 920 times 273.
Oh, where I just ditched my calculator.
Are you with me? There we
I'm
go.
back.
There's your calculator.
There it is. I think I clicked something. Something weird. The writing is on my calculator.
Oh man.
Oh well, I can see through. Let's see. So you
That's
did
good.
920 times
920
273.
times 273, right?
All right, I want to do the same thing. 920 times 273. And I hit enter first.
Right.
Now we'll divide by our third term.
So divide by the third term of 760.
Yep. So divide by 760 and hit enter.
Yes.
All right, I got 3,304.7. Wow, I got a lot of numbers. Do I get to keep them all?
Did I miss hit a button there?
Oh,
I
no.
got 330.
Look,
Oh, we
I did
had 760.
76.
There we go. I think the decimal is just going to go over one spot to the left there if we put that 760.
Right, probably so. I wonder, can I just go back to that step?
Is there an undo on that one?
No. Here's what I'll do to undo it. We'll multiply by 76.
That works.
Okay, now I'm back to this. Divide by 760.
Divide by 760.
Gotta hit all your buttons, and it works a lot better.
There we go.
Hey, does that match yours?
That matches mine perfectly.
All right. Do I get to keep all these numbers?
Let's see, what's our significant figures?
I can't see them now. Let's see.
See,
3,
920
3, 3.
looks like 3.
Yeah.
So
Should we count this 0 as significant? You think they're just being sloppy with
with
sig
the
figs?
920,
Yeah, let's count it as significant.
Let's
So we'll
count
go
it.
with 3. And then maybe when I fix the notes for next year,
you can put the
I'll put a
decimal there,
decimal there so we know.
so we know
Go
that
ahead and count it. Yeah. So our T2 is going to be equal to,
round that up to
come on,
300.
pig.
There we go.
330.
30.
And we can't round up to 331 because
Nope.
the 4 is not big enough.
Nope.
330 kelvins. Now,
There you go.
an important step here is to consider what we started with and see, does this make sense? We started at a lower temperature than that, right?
Right? We did.
But our pressure increased.
Yes.
So does it make sense then that when the pressure increased, our temperature should increase?
Right. Because if the temperature increases, we're going to have those more collisions.
Yeah, it's
pressure
directly
is gonna hurt more.
proportional. Yeah. So that makes sense to me. I think
Right.
we're good with that. So you
Yeah.
always want to ask yourself, does
Does it
the
make
answer
sense?
make sense?
That's a good thing to
Okay,
do.
look, I'm going to clear the writing before we move on. to
Oh,
the next
look at
slide.
that.
I'm learning. But where did my other arrows go? That's why I thought things were kind of goofy looking. Now I don't know how to advance my
We have the
slide.
arrows on the smartboard, but not on the... Oh,
Let's
it's
see.
kind of fadey out there.
Yeah, that's not the same arrows as what I had before.
It's not. They changed.
But it worked. I
It worked
used
still.
it, and it still worked. Okay, here's our last one of our gas laws. It's called the combined gas law. And basically, we're saying no matter... Uh-oh. Go back. I think that was just a delayed response. Double click. Okay,
There we go.
double clicking works.
Double
Single
click.
clicking doesn't. Learning my lessons here of how
Nice.
to do a podcast. Okay, so combined gas law says no matter what the change in the conditions are, as long as the number of moles remains constant, then we can predict what the new conditions will be. So you can change one of these factors, or you could change 2 or 3 or 4 or
Or,
whatever.
yeah,
And
whatever.
we can predict what the new conditions will be.
So the only thing that stays constant is the number of particles.
Right. So we've got to have more information, right?
do.
We have like these 3 different
Variables.
variables.
Right.
Their problems are going to contain more information. So if you see all kinds of information, you might suspect that it's going to be, hello, Pen. We might suspect it's going to be
There
the
it is.
combined gas law. I don't know what's going on, but here, let's fix this so that I have more control.
There we go.
What do you want from me now? Okay. See, having the laptop right in front of us kind of helps.
It does. It was just in a hurry to get to some practice, I guess.
I think so. I think I was in a rush, perhaps. Or you see this thing to click on my pen? Sometimes I hit that on accident and
Oh,
it
yeah?
changes things. All right, we have 256 milliliters of propane. That's a volume.
Yes?
Let's call it V1.
B1, sounds good.
And it has a pressure of 720 torrs. So 760 torr would be standard pressure. It's a little bit less than that, right? So we might
Right.
be in Falcon for this experiment because
It could be.
Falcon is not at sea level.
No, it's not.
We're at lower pressure
We're up
than sea
high.
level. And then a temperature of 25 degrees Celsius. We'll have to change that to Kelvins
Looks
before
like
we
it's
solve.
temperature 1 too, right?
Yeah, we'll call that T1 because these are all together.
Yes,
Oh,
right.
look, here's that keyword. Initially.
Good word.
Right. Okay, then what pressure? That sounds like a question.
Yes.
That's what we're solving for. What pressure will it be at when the volume decreases? Oh, I left that there. Oh, I don't want my phone to ring now.
Want your eraser?
Let me just click on it and I'll get to it. I'm done with the ringing.
There it is.
I just hung up on my cousin. Poor guy. All
You'll
right.
understand that you're on something really important right now.
I'm sure you will. If I had the ability to edit, that would be edited out. But I don't. So now everyone knows. I got a phone call. Now let's call this V2. Shoot.
I wonder who that is.
I know. Let's just try mute. Okay. It's quieter anyway. And here's our temperature. T2.
Right?
And we're trying to solve for the pressure. This must be our new pressure, right? We'll call that P2 that we don't know. And our combined gas law has all of the ones together.
Right?
And remember I said temperature is always in the denominator?
Right?
That's still true.
So true.
Put it
Doesn't
in the
change.
denominator. Right. And then we have P2 times V2 over T2. So far, so good?
So far, so good.
All right, now we can use the cross multiply method.
Right.
There's a lot more numbers, so we have to be more careful, but that's okay. We can do math,
We can. We
and
can
so
do
can
it.
our students.
Yes.
Do you want to change milliliters to liters, or are we the same in both?
We're the same in both.
Okay, then there's no need.
Yes.
So let's
Do we
just
want to
start.
change? Do we want to change our Celsius?
Oh, good thinking. Temperature 1 was 25, and I know that one by heart. 25 plus 273 is 298 kelvins.
There we go.
All right, now let's do 50 plus 273.
50 plus 273.
Oh, thanks for running the calculator.
Okay, there we go. On the calculator. We got 323.
That would have been my guess, because I can do math in my head.
Yes.
Yeah, but I like to do math
too.
that's easy. Thanks for running the calculator.
Sure.
All right, P1 was 720 torr.
Yes.
Oh, we don't need to write units in, because it won't have any meaning
It
here.
doesn't have any meaning.
All
We're
right.
just going to multiply and
720.
divide.
And then we're going to multiply that by V1, 256 milliliters. And that's all over
T1.
this T1, which we converted to 298 kelvins.
298.
Okay.
Okay.
So now we could do this as we set it up, right?
We could.
Multiply this and then divide by that and have one number here and another thing there.
No.
We could do that.
Right.
Or we could use the proportion thing. So let's take our pressure 2.
Pressure 2, which is
what
what
we
we're
don't
looking
know.
for, right?
Yep. And we're going to multiply that by volume 2, 250 milliliters. And divide by T2, 323 kelvins. Oh, my geez. Yeah, writing with this little tablet thing is a trick. My students make fun of me, and they should, because it's bad. All right, so
It's all a learning experience, though, right?
we're going to take these two and multiply them together, right?
Right.
And then we're going to divide by this third number for our cross-multiply thing to solve a proportion. What do I do with this?
Well, we want to get, that's multiplying by P2, so we want to do an opposite operation, right?
Right, okay, so then when we're done doing the division here, we can divide by this one.
Divide by the 250.
All right, well, let's do it. Let's see if I can bring my calculator back without any fuss. There it is.
There it is.
And all my
There are the
writing got
numbers.
it.
Can we see through it?
Ah, complicated here. Let me just move the writing off of it, if I can. See,
Yay.
all set. Turn it
Perfect.
on, and let me get rid of that, because I get confused when there's too many numbers on my screen.
Yes.
I need to move this too. Move that writing out of my way. All right, 720.
720 times 256 first, right?
Oh, look, I accidentally pushed 8s when I was trying to delete stuff. Okay, 720 times 256,
Yes.
right? Because they're together.
And
This
then multiply.
pen is going a little out
Oh,
of
wow.
control. Sorry.
Oh, no problem.
Back to the calculator. I don't know where it went. I think.
It's hard to see that with all that writing, isn't it?
Oh, okay. So go back. 256. Sorry for you guys trying to follow along at home because my pen is slow and sometimes I am too. All right, so we multiplied that and then we're dividing by 298.
Divided by 298.
Right, because that was this part of our calculation.
Exactly.
And I'm going to hit enter. But then we said, over here's that 250.
Yes.
We're going to divide by 250 so that we can isolate P2 and get that guy all by himself. That's how we solve this equation. P2, did you get the same answer?
I did. I got the same thing you did on my calculator.
Okay, let's keep here 2 sig figs, it looks like.
Looks like we're at 50 degrees Celsius and 25 degrees Celsius.
Yeah.
They both have.
Oh, how do we
And
round
we have that.
799 to 2 sig figs?
We have a 9, so that means we're going to have to go 3 spots over.
Right. So if we called this 800, it would not be clear that we mean 2 sig figs.
Right.
We're going to have to use scientific notation here.
We are.
8.0, that will be times 10 to the second. My writing.
Going right to the number there.
Yeah, let's see if I can get rid of that for all these folks who are trying to figure out what we did. Oh, but it's going to ditch all of that. Oh, well. They saw it, and here's our answer.
It is, and now we know that we have 2 significant digits there.
Right, but this is just a naked number that
Right.
has no units.
Right.
No naked numbers are
No,
allowed.
exactly.
That's not school appropriate.
So
Unity?
No, it's not.
Our pressure was in Tor before. I think we better keep Tor.
Tor is good.
Good. Put a box around your answer. You know why?
So we can see the answer.
Yeah, well, my students know the answer to that. You put a box around your answer because that's the way I like it. So I can see it. Yeah.
That's the way.
Right. And there's always someone in my class who has to sing to me.
Oh,
I
yes.
think we're done with this podcast.
Wow.
I know. I forgot. Double click.
Well, gas
Here
laws
we
are a
are.
piece of cake, aren't they?
I think we can handle this.
I
It's
think
all
so.
like proportions.
It is.
We can do this. And here's the homework that we're going to do in class. Actually, this is not the homework. We're not going to do this worksheet, but we have some other practice worksheets to do
Okay.
and some problems in the book. We have practice problems in the packet for the kiddos.
Right, exactly.
But we have some demonstrations to do too in class.
Yes.
Yeah, the gas
Can't
demonstrations.
wait. Can't wait to see those.
I know, me neither. So we better let these guys go. This has been kind of a long podcast, probably the longest one in this unit. And I really appreciate your help, Mr. White.
Absolutely. Thank you for doing it with me.
Sure. Where's the recorder? There it is. I went past it before. We gotta hit stop.
Have fun with your practice problems.
Yep. Bye, guys.